Okay, ladies and gentlemen, I hope you had a good break. So please join me in welcoming Stephen Shladover to the podium. Stephen is going to talk to us about truck platooning.
Okay, thank you. I'm going to describe some of the work that we've been doing in truck platooning. This is likely to be one of the earliest applications of cooperative automation systems. So systems that automate some of the driving function and make use of vehicle-to-vehicle cooperation. So I'll start first by saying what it is we're talking about, and then I'll get into the SAE levels of automation. When we start talking about automated vehicles, people often get really confused because there is so much hype floating around on the internet, and there are many different types of automation that automate different amounts of the driving function, but they all tend to get mashed together when people talk about vehicles being driverless or self-driving or other such terrible terms. And then I'll explain why I believe the vehicle-to-vehicle cooperation is really essential, and I'll show you some results that indicate how the lack of having vehicle-to-vehicle cooperation can actually make things considerably worse than they are today. But then I'll get into what are the benefits. If we can do this, if we can get the cooperative automation working, how is it going to help improve transportation? And particularly when we get into truck platooning, the major theme is energy saving. And I'll talk about why that is so important, and then describe what a cooperative adaptive cruise control system is, and then show some pictures and videos of our test trucks in action and some of the experimental results showing how much energy we can actually save when we operate those trucks in a cooperative platoon. So, what is truck platooning? Well, it's operating the trucks in really close formation using automatic control of the speed of the trucks and taking advantage of vehicle-to-vehicle communication to coordinate those speeds. So we have data that is broadcast by each of the trucks, and the other trucks can listen to that data and can adjust their behavior accordingly. We have been doing work recently on the cooperative adaptive cruise control version of this, which means it's an ad hoc combination of trucks. So any truck can enter or leave whenever the driver wants to. So the platoon can get longer or it can get shorter depending on where the origins and destinations are of the different trucks. The drivers have that as their option. And the separation between the trucks is governed by something called a constant time gap. So that means that the separation, the distance, scales with speed. As we get faster, they go a little bit further apart. As they get slower, they get closer together. That more closely replicates the way people drive. Another way of doing this is what we call the tightly coupled platoon. And we've also done experiments on this in previous years. This is a case in which the first driver supervises the operation of the followers, and the joining or the departing from that platoon would have to be authorized by the leader. So they stay together unless the leader says that somebody can enter or leave. And typically they operate at a constant spacing or constant distance gap. With that mode of operation, we can actually get them closer together, but it's also more challenging to get them to be controlled smoothly and accurately when we do the constant distance gap. So I said I would talk about the SAE Automation Levels. This is a document goes under the number J3016, was published last September, and unlike most SAE standards, this one is available free. You can download it online from the website address that's listed there. And this was developed by a task force of the SAE, of which I was a member. There were about 8 of us who worked on that, to try to categorize the different driving automation systems based on what portion of the driving is done by the system, what portion of the driving is done by the driver. So there's a series of questions here. Whether the driving automation system performs either longitudinal or lateral vehicle motion control, but not the other. And if it's just one of those, then it's a level 1 automation system. So adaptive cruise control is an example of level 1. Then second is whether the driving automation system performs both the longitudinal and the lateral vehicle motion control. If it does both of those, it's at least level 2. Then we have to ask some more questions. Does it also perform object and event detection and recognition? That means not just steering the vehicle and controlling the speed, but watching out for any hazards in the driving environment and responding to those hazards, which might be other vehicles, they might be loads that fell off trucks, could be any number of other things that represent a safety hazard. If the system also does that, then it's at least level 3. Then the other question, number 4, is whether it also performs dynamic driving task fallback. So fallback means the ability to recover from any bad event. So if it has that fallback capability, then it's at least level 4. Level 4 is the first level at which it's really possible for the driver to disengage from the driving task or for a vehicle to operate with no driver on board. And then finally, whether the driving automation system is limited by an operational design domain. So an operational design domain means the whole combination of weather conditions, road conditions, traffic conditions that make driving complicated. If there are any limitations based on that, then it is below level 5. So it only gets to level 5 if it's capable of driving under the full range of conditions in which people drive. And those level 5 systems are the ones that I would say we're not going to see in any of our lifetimes, and that includes the youngest person in the room, not just old guys like me. So what type of systems would exist at each of those levels? At level 1, you could have an adaptive cruise control system, or you could have a lane-keeping assistance system that steers the vehicle while the driver performs the other function. So at level 2, you could have the combination of adaptive cruise control plus the lane-keeping assistance. And there are a variety of those systems on the market already. By the way, level 1 is pretty widely available in a lot of cars now, including mid-range cars. Level 2 systems are only available on a limited number of high-end cars. That's what the Tesla system is, for example, but Mercedes, Infiniti, Volvo have them. And just about every other major vehicle manufacturer, if they don't have it right now, they'll be introducing it within the next year. There are also parking systems that will allow the vehicle to park even after the driver has gotten out of the car, but this is a case in which the driver needs to stand very close by the vehicle, either holding a smartphone or some other mobile device to be able to intervene if there's any kind of a problem to stop the parking maneuver. So this is a case where the driver has to monitor the driving environment to ensure safety because the system does not have the capability of ensuring the safety under all conditions. Level 3 is the first level at which the driver might be able to disengage temporarily to read a book or text or surf the web or other things like that. But the driver has to be prepared to intervene on very short notice when the system gets in trouble. Level 3 is very controversial. Most vehicle manufacturers do not believe it's possible to design a safe level 3 system. But Audi's going to stick their neck out later this year, and they're going to introduce a system that they call a traffic jam pilot. So that's something that could operate on a freeway within a limited speed range, I believe no more than 30 or 35 miles per hour. So the driver, if you're stuck in congested traffic, you might be able to do some of those other things while the car maintains control of itself. And then the hope is if a bad situation ensues, the car could at least stop itself without anything, any safety problem. Level 4 would be a situation that allows a wider range of conditions because it has the fallback capability. So the driver does not have to be available to regain control when something bad happens. The driver could even go to sleep, but it's still only designed to operate within a limited operational design domain. So it might be only on a freeway in free-flowing traffic, or it might only be on a freeway in very dense, low-speed traffic, might only be in limited weather conditions. Maybe it'll do it in fair weather, but not in rain, not in snow. This is the also level where we could have a platoon of trucks in which the following trucks might not have a driver on board. They could follow the leader, and although you would have a driver in the leader, the following trucks might indeed not have a driver on board. There are also many people developing low-speed urban passenger shuttle vehicles that could operate within very constrained locations, like, say, pedestrian malls, that would be at level 4. And the idea of valet parking systems that allow the vehicle to go and park itself even while the driver is not supervising them. And finally, to get to level 5, we'd have the taxi that can take you wherever you want to go, or the truck that could do a delivery run without any supervision, could drive anywhere, and then the drivers would not be needed at level 5. For any of these, I believe communication-based cooperation is going to be essential. You need that data coming from sources other than the sensors on board the vehicle, because you need information that may be beyond the line of sight for the sensor, or it may be type of information that no sensor is able to detect. So for example, if you're approaching a traffic signal, you might have a vision sensor that can detect whether that light is red or green. It has no way of knowing how many seconds remain on that red or green. But with communication from the intersection, it can tell the vehicle how many seconds are left on the red or green cycle. This helps to coordinate vehicle actions also. So vehicles can communicate with each other, and especially when we're in a vehicle following mode, if there's an acceleration command or a braking command to a vehicle in front, the vehicle behind knows as soon as the command has been given, it doesn't have to wait for the speed of the other vehicle to change and for the sensors to be able to detect that that speed has changed. And I'll show you on the video why that is critically important. This has implications for traffic congestion, travel times, and energy consumption and emissions, because with the vehicle-to-vehicle communication and coordination, we can really smooth out the traffic disturbances. We can also get the vehicles close enough together that they can start getting benefits of aerodynamic drafting, and that becomes a big deal for trucks. With infrastructure-to-vehicle communication, we can also support broader traffic management functions, things like speed advisories. The Traffic Management Center knows what's the optimal speed for a particular section of roadway. That information can be communicated to the vehicles to be used as a set speed for the adaptive cruise control. Or if there's an incident, vehicles could be rerouted, or if there's a weather problem, vehicles could be rerouted to deal with those problems. Those are things that onboard sensors are not going to be able to tell you about. And particularly eco-driving is an opportunity if the vehicles receive advanced information about things like traffic signal changes up ahead or traffic flow problems further up ahead, they can start adjusting the speed profiles earlier and actually get to much smoother acceleration and deceleration profiles, and can even avoid having to stop at traffic signals if they have the information to know that they can coast through the traffic signal. So I mentioned the importance of the communication. I'm going to show a couple of videos here with adaptive cruise control. The left one I'm going to show first. This is now production adaptive cruise control on 4 vehicles. So they are autonomous, which means there's no communication between them. They're simply vehicles that the manufacturer has equipped with the adaptive cruise control. And what we've done is we've commanded a gentle speed change profile to the first vehicle. And then we'll have the followers. So the lead vehicle is now accelerating at 0.05 Gs, and the followers are trying to keep up with it. And then it'll go to a constant speed cruising. Now it's at constant speed cruising. Notice we got braking on the 3rd and the 4th car. Those are left over from some earlier disturbances. Now the vehicle's decelerating at 0.05 Gs, and the sequence of brake lights took 5 seconds to get to the 4th vehicle. We'll see this again. Now they're at constant speed again. Then we're going to repeat the maneuver. The lead vehicle accelerates at 1/10 of a G. This is still a fairly gentle acceleration. 4th vehicle's got its brake lights on because it's still oscillating from the previous disturbance. Now they're at constant speed, and now watch the brake lights. Decelerate at 0.1 G, 2nd car, 3rd car, 4th car. That's a 5-second delay after the braking of the 1st car. That is a traffic flow instability in the making. This is much worse than it would be if people were driving the car. I mean, I rode in the last car in that. You would not want to be driving in that car. The performance is so bad, you'd turn the system off because it's not responding properly to what's happening up ahead. That is a consequence of the sensors only seeing the vehicle immediately in front of them, and the sensors have serious delays built into them to do their signal processing to actually verify whether the distance to the vehicle in front has actually changed. So all of that adds up to a 5-second delay to going through the sequence of 4 cars. So we took the same cars, we added vehicle-to-vehicle communication, and we modified the controller for the speed. Now we can go in shorter gap. We do the same maneuvers now. So now we are able to go at 0.6 of a second gap instead of 1.1 second gap. Lead vehicle's accelerating at 0.05 Gs once again. Then it's constant speed. Now lead vehicle's decelerating at 0.05 Gs, and we got no brake lights. That's because at that gentle deceleration rate, we just do it with engine braking. All I had to do is back off on the gas, and the cars slow down at that rate. Now we're going to be constant speed. Then we're going to do lead vehicle accelerate 0.1 G. Notice they all start pulling away from our chase vehicle. And then they'll be at constant speed. So now they're constant speed, the higher speed. And then we're going to do the braking. And so you get all the brake lights coming on together because the communication system on the first vehicle communicated that braking information to everybody as soon as it happened. They all received that, and then they all responded. By the way, the distance there, this is a time gap of 0.6 seconds, which is much shorter than the minimum gap that's available on production adaptive cruise control systems. But if you're driving in an urban freeway condition, that is not an unusual gap. That's something you frequently encounter. So often when I talk about 0.6 seconds, people get all excited and think, oh, that's so terribly close, so terribly dangerous. We've taken lots of visitors for test drives on the car, and almost everybody gravitates towards that short gap setting. So the test data, what we were showing on the video was the second half of these plots. So on the left side, the one without communication, you can see all the oscillations. Indeed, when the first vehicle was braking at 1/10 of a G, the fourth vehicle was braking at 3/10 of a G. We got an amplification factor of 3. On the right side, you see the smooth profiles because with the cooperative system, they were all driving in sequence with each other. So what type of benefits could we gain at each of the automation levels? This now assumes we've got that communication to enable cooperation, because if we don't have the communication, these benefits go away. So level 1 will get some comfort and convenience for the driver. We should have some substantial energy savings, both from smoothing out the speeds, as we showed here, and also from drafting, which I'll show in a few later slides. And we should get some safety, because we're providing collision warning information to the drivers to help the drivers better avoid collisions. At level 2, we could get some additional comfort and convenience. We could get additional energy savings if we get the vehicles closer together. So if we get really close together, we have to automate the steering as well, because it's too hard for the driver of a following truck to steer if they get really close to the leading truck. But there might be a reduction in safety if the system is misused by the driver. And there's a lot of evidence of drivers misusing level 2 systems. They treat them as if they're level 3 systems. Indeed, several Tesla drivers have died because they assumed that their level 2 system on their Tesla was a level 3 system, and they stopped monitoring and paying attention. And when the system encountered a situation it couldn't handle, they had some real serious crashes. At level 3, you've got the potential for the driver to do some non-driving tasks. So think of the truck driver who can now become a logistics manager. He can be communicating with his dispatcher. He can be communicating with his customers because he doesn't need to pay constant attention to what's going on the road. But if the driver is not able to re-engage with the driving task and maintain their vigilance, we could actually have a reduction in safety. At level 4, now the driver can actually do all those other things without any safety hazard, because at level 4 the system has to have all of the built-in backup capabilities. So this really improves the driver's quality of life, turns that driving job into something much less stressful. In trucking, the hours of service restrictions are a really big deal, so there might be an opportunity to reform hours of service regulations so drivers can actually be on the road for a longer period of time. That's where you get the possibility of driverless followers in a platoon of trucks, which can save labor costs for those following trucks. And because there is built-in fallback capability, there really should be some enhanced safety. Of course, at level 5 in the very remote future, then you wouldn't need drivers. But I always tell people, don't worry about any drivers who are driving today. This is not going to happen. They'll be able to retire before level 5 becomes a reality. They're not going to lose their jobs in the next 5 or 10 or 15 or 20 years. Yes, really. So when we get to heavy trucks, energy savings are really important. Heavy trucks consume about 20% of all the energy used in transportation in the U.S., and they consume about 14% of all the petroleum that we use in the U.S. From an individual truck operator point of view, fuel represents 39% of their operating costs when they're doing long-haul driving on the highway. So if they could save 10% of the fuel costs for a long-haul truck, that's on the order of $6,000 per year, which could be worth $60,000 over the life of the truck. Well, these systems, at least the level 1 systems of the type I'm going to show you, won't cost anything near that. So there's a big return on investment. So we've been doing some work under the Federal Highway Administration's Exploratory Advanced Research Program, together with the California Department of Transportation and Volvo Trucks, and we've actually implemented a cooperative ACC system on 3 Class 8 trucks. And then we've measured the energy saving that we can get on the test track, and in the next couple of months we'll be doing some experiments with drivers to determine what their preferences are among the different available gap settings. We're also simulating what the impacts are going to be on traffic and energy use in a high-volume freight corridor. So the Cooperative Adaptive Cruise Control System starts with a production adaptive cruise control that's already on the Volvo truck, and we've added a couple of antennas for the DSRC communication system as well as the DSRC radio. So that communication includes the vehicle location and the speed and the acceleration and the braking commands. This enables the trucks to operate at 4 different time gap settings that are shown there, from 0.6 to 1.5 seconds. And I've listed what the distances are when we're at a speed of 65 miles per hour. And then this also includes coordinated braking. So if any of those trucks supplies the service brakes, then that braking command goes to all the trucks behind. There's also an emergency disengage button in case any of our stuff doesn't work right, the driver can disengage. And there's a supplementary display that tells the driver the mode the system is in. It shows the status of the other trucks that they're coupled with. It shows what the gap settings are, so the little arrow buttons are used for the driver to select whether they want to get closer together or further apart. The red border around the truck icon tells the driver that that truck is actually applying the brakes, and little green arrows show which position this particular driver is in. So they know where they are relative to the others, and they know if anybody is braking. There are also some icons to indicate if there are any failures on any of the trucks. So we did a series of very careful experiments this past fall in collaboration with Transport Canada and the National Research Council of Canada on a test track north of Montreal, following an SAE standard test procedure that's very rigorous. Each test run is a 64-mile continuous run, 16 cycles around this 4-mile track. And then we do 3 of those runs under the same conditions and average all the results to get fuel consumption measurements. And the fuel consumption is measured by weighing the fuel tanks before and after each run. So there's an auxiliary fuel tank, which you can see with one of the researchers off on the right, that gets weighed by the forklift truck that has a load cell at the end of the fork, so that it's weighed before and after each run to measure how much fuel was consumed. Transport Canada was also really interested in how does this combine with side skirts and boat tails on the trailers as an energy saving. So we did tests with standard trailers and with trailers that had the aerodynamic modifications, which are shown on the truck on the left. And then show the video from that test track testing. Let's turn the sound off. This is in Blainville, Quebec. That test track is owned and operated. It's owned by Transport Canada. It's operated by a company that works very closely with them. So this is an 18-wheeler, an over-the-road with big sleeper cab configuration. And here you see them on the track. This is at the 0.6-second gap. So that's the minimum gap of the gaps that we tested. We tested them driving individually to set the baseline. Say that's the baseline fuel consumption when they're not coupled together closely. And then we measured the fuel consumption under these different conditions when they are coupled together using the cooperative ACC system. So we don't need to continue more of that, but let's go to the data. So first of all, with the standard trailers on the left side, the lead truck didn't save any energy. The middle truck was saving between 6 and 7% of its fuel, and the following truck saved between 10 and 11% of the fuel. When we added the aerodynamic modifications, it turns out those savings were additive. So we got the savings from the aerodynamic treatment plus the savings from driving close together. And you can see on the right side, those savings range from about 12.5% to 14%, depending on the gap. Now, we need to do more experiments at both longer gaps and shorter gaps to fill out both ends of that curve. And in fact, we're going to do some of those experiments this coming summer. So, main findings from this. With the standard trailers, the trucks can save about 5% on average. When we average together the results from the first, second, and third truck, it came to about 5%. With the aerodynamic trailers, that grows to 12 to 14% compared with the standard trailer solo driving. In this range we were testing, they're not very sensitive to time gap values. The lead truck saves very little, if any. The third truck saves the most. Other experiments that we and other researchers have done have shown when you get closer together, the lead truck also saves some energy. So the effects of the short gaps and the aerodynamic trailers actually reinforce each other, and then we're going to go on and study both shorter and longer gaps this summer. So with that, I can conclude my prepared remarks, and we'll see if there are any questions I might be able to answer. Yes?
Is there any traffic implications to having these trucks stacked together and not allowing cross-flow traffic if someone needs to exit?
Yeah, so there are traffic flow implications when we get the vehicles closer together, and there are two effects that work in opposite directions. So one is if they're too close together, then that impedes lane changing by other vehicles. But if we don't have them close, if they have them closer together, we actually get a higher volume of traffic throughput. So we've been doing some really detailed traffic simulations on that to try to see how those two effects balance each other. But I will tell you, even when we drive at that minimum gap that you saw in the video, we do that on public freeways in California. We've got people cutting in between us all the time. People will cut in between when we're near on-ramps and off-ramps. So at an on-ramp, somebody wants to get into the freeway, they will come into the 0.6 of a second gap. We're nearing an off-ramp, somebody didn't get in the right lane early enough, they'll cut right between us to get to their off-ramp. So. Yes, so the system detects the cut-ins and then it will back off. And because those vehicles are unequipped vehicles, they're not telling us what's going on, we have to allow a larger gap behind them. And then after they've left, we rejoin with our leader and reform the platoon. Now, of course, we've lost energy savings during all the time that we've had the cut-in. This is one area in which we, of course, want to test with a representative sample of drivers from the general driving population to see how much that affects their preferences among the different gaps. So we'll give them the choice of the 4 different gap settings and then record how much time they prefer to use the system at each of the gaps, and we'll have a questionnaire that will ask them about their preferences among the different gaps. Another question? Yeah. Yes?
What's the average cost of the system you've implemented?
Well, of course, the system that we've implemented is a prototype system with custom-built hardware, so that's not reflective of what a production system would be. The hardware that goes beyond what's in the production adaptive cruise control is simply the DSRC radio and the antennas. The DSRC radio for our test cost us about $3,000 each, but assuming that the NHTSA mandate goes forward and those will be required on all new cars in a few years, those will be down to a couple of $100 each. The antennas right now cost us a little over $100 each, and again, I expect those will come down in cost as these things get more widely used. So it's not a huge cost increment. But is there one? Yeah.
You showed the braking communication in those 4-passenger cars, where there may be a difference of a few hundred pounds between each vehicle, but with straight trucks, 53-foot kingpins, where the size difference could be tens or thousands of pounds. Does the communication take into account that one truck may need a drastically different braking profile?
Yes, and the information that they can exchange can include the mass of the truck. And we've also talked about strategies in which you maybe put the heaviest truck up front so that the one that's least capable of braking is ahead of the others, and therefore you're not going to have a truck in front braking harder than the followers are capable of braking. That's still under discussion in terms of how the trucks get sequenced when they get put together. The other possibility is limiting the braking on the leader so that it is no more than the braking of the least capable follower, unless they get into a real emergency situation. I know I'm getting a time signal, but let's see, maybe you have one more?
How about CAT scale data?
How about?
Well, every time you go into a different state, you got to go to CAT scale.
Yeah.
So update that, you have to update the truck for what it is, and then update your.
Well, in fact, these trucks already, the question was about the weighing, the weight of the truck and being able to know the weight of the truck. The transmissions on these trucks already do an estimate of the mass of the truck. So it's already built in. We can actually get that off the onboard CAN bus. And it's a pretty decent estimate of the mass of the truck, yeah. So that's actually not a problem. We do know the mass to a reasonable accuracy.
Theoretically, how many trucks could be in a row?
Theoretically is not the right question. How many could go in a row? I don't think it's a theoretical question. It's a practical question. The most that has been done in any experiments I've seen have been 4 trucks. And I don't see any reason why you'd want to go to more than 4 trucks. If you get to longer than 4 trucks, you're not really getting any benefit in terms of your energy savings. You've already kind of maxed out on your energy savings, and you now get into more of a problem with the potential interference with other traffic and impeding the lane changing by other vehicles. You also have a logistics challenge of how do you actually get 4 trucks that are heading in the same direction at the same time that want to couple with each other. We did a survey of truck operators a number of years ago to see about their willingness to delay their departure so that they could couple up with others. Nobody really wanted to delay a departure by more than 5 minutes in order to have the opportunity to match up with somebody else. So that's actually a limitation when there's still a relatively limited population of the equipped trucks. So with that, I think I need to thank you for your attention and